Okay, so let's move on to the first palette sparsification theorem given by Alon and Assadi. This is the sparsification theorem in the 1 plus epsilon times delta regime. The theorem states that for every epsilon greater than 0, there exists a number n0 such that for every given graph G with sufficiently large number of vertices, and the number of colors in the global palette is 1 plus epsilon times delta. Note here that this epsilon need not to be less than 1. It could be 1 or 2 or much larger than that. So if the graph has individual list independently and uniformly random sampled from this global palette and is of size the square root of log n over epsilon to the third, then this graph is less colorable from those sampled lists. Okay, so to compare this with the delta plus 1 regime, in the delta plus 1 regime, the soda paper showed that we can get a coloring or palette sparsification by sampling of log n colors in each individual set, and they showed this is actually optimal. In this 1 plus epsilon times delta regime, well, here we only need to sample a square root of log n for fixed epsilon. And as we will show later, this is also asymptotically optimal. Well, this actually shows that allowing more colors in the global palette can drastically improve the improve the result and reduce the number of samples that you need. Okay, so to prove this theorem, we will rely on one of the previously known result by Reed and Sudakov. So let me define, before we describe this lemma, let me first define a notion called C degree or color degree. C degree is defined as degree, okay, for a set of list S. The C degree is degree V for vertex V and color C V in V. This is defined as the size, the cardinality of the set. Okay, UV is an H, and this color C is in the list of V. Sorry, U. Okay, so if you have like a vertex V and you have many other vertices, U1, U2, U3 are neighbors of V, then this C degree counts how many neighbors of V are have this color C inside their list. And if the C degree of this vertex V is large, then it would imply that choosing C for this vertex, choosing color C for this vertex V would likely result in a conflict, and vice versa. So Reed and Sudakov's result says that for every epsilon greater than 0, there exists a D naught such that for large enough D, if the graph has list that has a large, this is saying this is a large list size, is greater or equal to 1 plus epsilon times D, and for every color C, the C degree is small. Okay, if you have large list size and a small C degree, then G is least colorable from this set S. The proof of this theorem uses Rudolph's nibble method, and we'll show this in the second part of the video, so I'll skip this for now. Okay. Now let's move on to prove the 1 plus epsilon times delta regime Pallas sparsification theorem using the Reed-Sudakov's theorem as the lemma. Suppose we sample L equals to some constant, say 20 times square root log n over epsilon to the third colors per vertex. Then for every vertex and every color in the list of V, we have the expected C degree. This can be computed by the sum of all the probability for each neighbor, such that C is in the list of U. This is less or equal to the maximum size of the neighborhood times the probability, which is the sample size over the entire palette size, 1 plus epsilon times delta. This equals to L over 1 plus epsilon. We can make an observation here. So if the C degree LVC is highly concentrated, such that the maximum C degree is 1 plus theta epsilon times delta times L. Then we can apply Reed-Sudakov directly. Why is this the case? Well, let's look back at the Reed-Sudakov's lemma. Suppose we have this condition here. Then we can set this D to be the maximum C degree. And then the second condition will be automatically satisfied, because every C degree is less or equal to the maximum C degree. And if you look at the first condition, since this is this is 1 minus theta epsilon times L, then we will also have that the list of V, which has size L, is greater or equal to 1 plus epsilon times D. So the first condition is also satisfied. Thus, if we have that the C degree itself is highly concentrated, then we can apply Reed-Sudakov directly to get to get the main theorem. However, things don't go as things are not as desired. It goes as what we desired. So this is hypothetical. In reality, we cannot bound the C degree like this. and you can show that such a concentration fails. So what we can do instead here? Okay, so instead I can claim that there there is a subset L hat of V in in the okay the subset L hat of V in the LV set for every V, and the L hat is highly concentrated, and we can color from the L hat. Okay, so it's for every V, and the graph G is list colorable from L hat. Okay, so why is this true? Well, let's call a color C bad for vertex V if the C degree of vertex V is greater or equal to 1 plus epsilon over 2 times L over 1 plus epsilon. Okay. So since we sampled the list L of V independently, we can apply Chernoff bound. So the probability of the C degree is greater or equal to 1 plus epsilon over 2 times L over 1 plus epsilon is less or equal to some exponential tail. I'll use this to denote the number of bad colors for the vertex V. And now we want to bound the number of bad colors for V. So we use the following inequality. The probability that the number of bad colors for V is greater or equal to epsilon L over 4 is less or equal to L over, okay, it's less or equal to L choose epsilon L over 4 times exp minus epsilon squared over 12 times L over 1 plus epsilon to the epsilon L to the fourth power. Okay, so note that the right hand side of the inequality is the case where each color being bad for vertex V are independent events. So that's when we can take this to the epsilon L to the fourth power. But in reality, the color C being bad for V might not be independent from the event that some other vertex C prime is bad for vertex V. However, if a color C is bad for vertex V, then it actually reduces the probability that the other color C prime is bad for vertex V. So this dependency actually doesn't hurt the inequality, and the inequality will still hold. And this through some algebraic manipulations, we can show this is less or equal to exp minus 5 log n. And by union bound, with high probability, with high probability, for every V, the number of bad vertices for V is less or equal to epsilon L to the fourth. This is a standard union bound. Now we can finally remove the bad colors from the list LV and obtain a good list where there is a concentration and with which we can apply Reed-Sudakov's lemma. So let L hat V be a subset of LV where we remove all the bad colors in LV. Since we just showed that the number of bad colors for V is less than epsilon L over 4, this would mean that the size of the L hat list is greater or equal to L minus epsilon L over 4, which is 1 minus epsilon over 4 times L. Okay, so on the other hand, for every vertex V and every color C in the list of V, the C degree in this L hat set is less or equal to the C degree in the original L list. This is because the subset L hat has a smaller number of colors, and thus the number of vertices that are neighbors to V decreases. And this is less or equal to 1 plus epsilon 2 over 2 times L over 1 plus epsilon, as we've shown earlier. Okay, and when epsilon is less than 1 over 2, this is less or equal to 1 minus epsilon over 3 times L. When okay. So now we have these two conditions. So we can actually, to apply Reed-Sudakov's lemma, we can simply set D equals to 1 minus epsilon over 3 times L. And then we would have that and then the first condition is satisfied because L hat V is greater or equal to 1 minus 4 epsilon over 4 over 1 minus epsilon over 3 times D. And the degree L hat of VC is always less or equal to D. So having both conditions, we can simply apply the Reed-Sudakov's lemma to obtain that to prove the fact that there is a list coloring in this L hat set. So G is list colorable from L hat. Since L hat is a subset of L, we can conclude that G is also list colorable from the original L set. Okay, and this finishes the proof. There are a few things I want to remark. First, okay, so I want to note here that we choose D to be 1 minus epsilon or 3 times L here. Recall that in Reed-Sudakov's lemma, we need D to be greater or equal to some constant number D naught. This D naught is a constant and it is only dependent on epsilon. So when we choose the graph uh, to be large enough, and since L is in the order of square root log n, when n is large enough, then this D will be larger than D naught. So that's why we can apply Reed-Sudakov's lemma here. Now let's show that sampling big O of square root log n number of colors for each vertex list is actually optimal for the path sparsification in this regime. As a comparison, in the theorem, Alon and Assadi show that sampling some constant c times square root log n over epsilon to the third is enough. And here, what we are going to show is that sampling some constant c prime times square root log n is not enough for palette sparsification in the 1 plus epsilon times delta regime. Okay, so the proof idea goes like this. We show that for delta, which is the maximum degree, equals to 1/2 times log n, square root log n, and L equals to 1/2 square root log n. Here we ignore the little constant, so there might be a plus some constants here. In the end, we just need to ignore that. And suppose the palette has 2 delta colors in the palette. Okay, so it's 1, 2, two delta. We show that there exists a graph G such that the sampling only L number of colors fails the palette sparsification task. Okay, so here's the graph construction. Suppose a graph G that looks like this. We have L plus 1 clicks, C1, C2, all the way to CK, where K equals to N over L plus 1. And for each click, we define the union of all the list of colors LCI to be just the union of all the list in CI. And okay, so the proof idea goes like this. If we can show that for one of the click CI, the number of colors we sampled in this click as a union of the list in this click is only L, then we cannot color this L plus 1 click. So more formally, we can describe it in this way. The probability of the list of CI is only 1 all the way to L. The probability of this is 2L, choose L to the minus L plus 1 power. Okay, this is because we are choosing we are choosing 2 delta equals to 2L 2 delta equals to 2L number of colors in the palette. We are choosing, okay, so this is because we are choosing L colors from the palette of size 2 deltas equals to 2L. And here's a parenthesis here. And we are doing it for all the L plus 1 clicks. So since the choice of colors across different vertices in the clique is independent, we have this equality. Okay, so then it is greater or equal to 2 to the 2L minus 2 to the minus L plus 1, and this is greater or equal to 1 over square root n. This is a very loose bound, but it's enough. Okay, when we choose L, since this is when we choose L equals to 1/2 log n, square root log n. Okay, so since the event is independent across the cliques, with high probability, there exists some CI such that the list is only consists of colors from 1 to L. Therefore, with high probability, there exists some clique CI that only consists of colors from 1 to L, and therefore it cannot be used to color this clique CI. And therefore we get a counterexample for the delta equals 1/2 square root log n equals L case. And since for some delta and L, 1/2 square root log n is not enough for coloring. That would mean that merely sampling O of square root log n is not enough to guarantee a palette sparsification result. This actually means that the serum sampling size is optimal up to a constant factor. Now let's move on to the discussion of streaming algorithm. For streaming algorithm, we'll prove the following theorem. There exists a randomized single-pass streaming algorithm for finding the 1+ epsilon delta palette coloring for any general graph within n log n space, which hides the epsilon constant factor. Okay, so as we've shown in the previous examples, the procedure of streaming algorithm as a corollary of palette sparsification goes like this. First, we need to sample every list L of V before the graph arrives. So this ensures that the sampling process is actually independent from the graph. Then, during the stream, when some UV edge arrives, we need to maintain a conflict graph. Recall that the conflict graph consists of G conflict is V E conflict, where E conflict are the set of edges in the original edge set, such that every two adjacent vertices in the conflict graph has a not disjoint color lists. Okay, so when UV arrives, we maintain this edge list for conflict graph. Maintain E conflict by LU plus LV is empty or not. Okay, then the last step is just to color the conflict graph. G conflict. Then the last step can be done with symmetric lowest local lemma or stuff for. So you can use Mozart-Tardo's algorithm. And algorithmic lowest local lemma, this should run in the number proportional to the number of edges here. Okay, so what remains to be shown is that the space needed for this algorithm is n log n. Okay, so to study the to study this, we only need to bound the number of edges. Okay, so we first need to study the number of edges in this conflict graph, and so more importantly, we want to study the probability that given some edge UV, their edgelets are not disjoint. Okay, so if they are not disjoint, then the probability will equal to the sum of the colors in U such that this color is also in the color set of V. Okay, and this equals to LU times LV over LU times LV over 1 plus epsilon delta. And this equals to L squared over 1 plus epsilon delta. So as before, this little l denotes the sample size. So L sample size. Okay. So now let's study the average degree of this conflict graph. So the average degree is expected degree of this conflict graph for a vertex V. This is the sum of the probability that so this is the sum of probability such that color. Okay, so you first fix some vertex V and V, and it's a sum of the probability that sorry, U in V such that LU kept by LV is not empty, right? And we've already know that this is less or equal to delta the maximum degree times the probability above, which is L squared over 1 plus epsilon delta, and this is simply L squared over 1 plus epsilon. Okay, so now we have this quantity, and what we can do here is to use turnoff bound. Let us expect the degree of the conflict graph be mu. If I turnoff bound, so we can apply this because the degree of the conflict graph is the sum of independent variables. Okay, so the probability of that degree of the conflict graph of V is greater than 2 times this expectation. So let's just use some constants. Some constant C times this mu is actually less or equal to the tail. So I just give the constant computation. So this is something like minus omega L squared. So notice that mu equals to theta of L squared here. And therefore we have that this equals to exactly e to the minus omega mu. Okay. Now let's use union bound. Okay, so by union bound we have that with high probability. With high probability or OV, the degree of the conflict graph V is less or equal to C times mu. Right. And okay, so and since mu equals to theta of L squared, this is just theta of L squared, which will mean the degree of every vertex V in conflict graph is O of L squared. Okay, then we can just like apply the handshake theorem or whatever it is. The the set of edges is 1/2 times the sum of all the degrees in the conflict graph. And this is exactly O and L squared. Since we chose L to be square root log to the third n, log n over epsilon to the third, this is exactly O n log n, hiding the epsilon factors. Okay, and this finished the proof of the streaming algorithm. Now let's move on to the sublinear algorithm setting. This is another corollary of the palette sparsification theorem, and it's a huge improvement. We're going to assume a model, a query model here. The model here supports the following types of non-adaptive queries. By non-adaptive, we mean that the queries are themselves in parallel. So they are in parallel. And you cannot just do a query, then do another query based on the query you did before that. So you cannot use the result of preceding queries. In this setting, we are allowed to query the degree of a given vertex V. We can also query the i's neighbor of a given vertex V. We can also query whether the two given vertices UV are adjacent. So for this problem, we're going to prove the following theorem. There exists a randomized non-adaptive sublinear time algorithm for finding a 1+epsilon delta palette coloring for any given graph in O tilde into the 3/2 time. Okay, so it is pretty important for this problem to consider the problem in two different regimes. The first regime is when the graph is sparse. Well, if the graph is already sparse, then and the number of edges is small, and the number of degrees is the size of the degree. Okay, the degree of the maximum degree is already small enough. Then you don't even have to do the palette sparsification thing. Okay, so this is the easy case, the sparse regime. In the sparse regime, okay, we say delta less or equal to square root n. Then we can read the entire graph. Right. We can read it with neighbor queries. Neighbor queries. Okay, and then we can do like a tiny filtering step. So we can just filter UV if LU and LV are disjoint. Okay. And after this step, every edge that is left is a conflict edge. And we can just solve it by the naive n times delta algorithm. So solve with naive and this is O into the 3/2. Okay, the second case is a little bit trickier. This is the dense regime where delta is greater than square root n. We can keep Okay, so in this case, we can keep a set of vertices for each individual color. So for example, we can set VC to be the set of vertices V such that C is in the color list of V. Right, and okay, and then the size of the conflict graph is less or equal to the sum of VC choose 2 for OC. And then the expected size of each VC is, okay, so be careful, there are n vertices in the original vertex set. And for every color, okay, so for every list, there are L colors and there are C colors in the palette. So this exact degree is just simply NL over 1 plus epsilon times delta.
Okay, so the total size of the sum of all the colors E of VC is just n times L. Now we are going to try to bound the size of the conflict edge set. So the size of this is exactly the sum of VC times over choose 2 for all the C, and this is less or equal to the sum of C VC squared, right? And then okay, so the expected we can take expectation on the right hand side, and this will be the expected CVC squared is equals to, right, so as we shown earlier, the expected VC expected size of the set VC is NL over 1 plus epsilon times delta. So here it will be NL over 1 plus epsilon times delta squared, and there are 1 plus epsilon times delta of them. So it would be actually looks like this, n squared L squared over 1 plus epsilon times delta. And this, if you take L equals to square root log n over epsilon to the third, you would finally get, okay, this is O tilde of n squared over delta, right? But in the dense regime, actually we have delta is greater than square root of n. So this is O tilde n to the 3 over 2. Okay, and that gives you a n to the, because so if we combine the two regimes, sparse and dense, okay, in total we get a O tilde n to the 3/2 algorithm for this graph G. And then we know that, like, since the original graph can have at most n squared number of edges, this n to the 3/2 is even better than reading the entire graph. So that makes this sublinear algorithm very efficient. Okay, so today we talked about sublinear algorithms and streaming algorithm as a direct corollary of the Sparsification theorem, and we also showed how Reed and Sudakov's lemma leads to the proof of the Sparsification theorem in the 1 plus epsilon times delta regime. In the next video, we'll talk about nibble method and some other proof techniques like Telegram's inequality. So that's all for this video.